Hello everyone, in this video we are going to derive the equation of a general conic section by starting from the equation of a cone, the vector equation of a cone, and then finding the intersection of that cone with the xy plane. So we're literally just taking a cone and taking a slice out of it, which is of course why conic sections are called conic sections. As part of our working, we'll also introduce something called the discriminant, which is a quantity you can define for any conic section. We will understand the geometrical meaning of the discriminant and hence derive some conditions that you can check given an arbitrary conic section equation to determine whether you've got a parabola or a hyperbola or an ellipse. Now, I actually had quite an interesting time preparing for this video because since I first came across conic sections many years ago, I had of course been aware that in principle you could get their equations by taking a slice out of a cone, but I had never actually seen the details of that, how to get from the definition to an equation. And from my research, it seems like it's not something that gets discussed that often. So for this video, I worked through all the details myself. So I hope it's going to be something a little bit different and interesting for you as well. So we need to start by coming up with an equation for the cone, which I have sketched on the screen here. A couple of parameters of the cone to make it as general as possible are that the vertex of the cone has a position vector r0, the half opening angle of the cone is this alpha here, and I've got a direction vector n, which just tells us where the axis of symmetry of the cone is, and we're assuming that n has already been normalized, hence the hat. Now, the defining feature of a cone really is that if you take the position of any point on the surface of the cone, let's just draw some arbitrary position as a dot there, and you take the displacement vector from the vertex to that arbitrary position there, that displacement vector will always make a fixed angle of alpha to either the vector n or the vector minus n if we include the branch of the cone down at the bottom there. Now, mathematically, the cosine of the angle between two vectors is given by the dot product of the vectors divided by the product of the magnitudes of the two vectors. And we can use that to come up with a vector equation of our cone. So the displacement vector, this arrow that I drew onto the cone up there, we can write as r minus r0, where r is our arbitrary position vector on the surface and r0 is the vertex. We're going to take the dot product of that with the direction vector n, the axis of symmetry. We're going to divide it by the magnitude of the displacement vector, so it's divided by modulus of r minus r0. We don't have to divide by the magnitude of n because we're already assuming that it's normalized, and that is going to be a fixed value of cos alpha. Now, actually, we really want to put a plus or minus on the right-hand side or on the left-hand side, it doesn't really matter as well, because we want to include both the upper and lower branches of the cone, right? The angle alpha is with respect to the vector n on the top of the cone, but it's actually measured with respect to the vector minus n on the bottom branch of the cone. And so that could either be positive or negative if we're including that entire cone. We can get rid of that by squaring both sides. So I'm going to move my equals over a little bit, put brackets around the entire left-hand side and make the right-hand side cos squared alpha, because then when you square root all of that, you automatically get that plus or minus. So before we basically take a slice out of this equation, I just want to do a couple of algebraic manipulations to get this into a form which is going to be more helpful for us. Firstly, I'm going to get rid of the fraction and also expand some of the brackets on the numerator and write the numerator as r dot n minus r naught dot n. That's all going to be squared. Then I'm going to take my cos squared alpha on the right hand side and multiply that by the squared modulus of r minus r naught. So let's expand out both the squared bracket and the squared vector modulus. The squared bracket is easy because r dot n and r naught dot n are both scalars, so you just get your first scalar squared, which is r dot n all squared. We're going to add on the second scalar squared, which is plus r naught dot n squared, and then you get twice the product of those two terms, which here is going to be minus 2 r dot n and then r naught dot n, so that's our expanded left hand side. Now for the squared modulus, remember that mod of r minus r naught squared is the same as r minus r naught dotted with itself. So you want to expand out that dot product, remembering that each term has to be preceded by a factor of cos squared alpha. Let's write down our cos squared alpha. The first term is going to be r dotted with itself, which is the same as modulus squared of r. Then you're going to have minus r naught dotted with itself, but it becomes positive because two negatives make a positive, so plus cos squared alpha modulus of r naught squared. Then your cross term is going to be a dot product because the whole of the right hand side is really a dot product. It's going to be minus 2 cos squared alpha times r dotted with r naught. Final manipulation I'd like to do with this equation is to put all the terms on the same side and to regroup them into a more logical order where similar terms are next to each other. So what I mean by that is, first you think about this first term. So r is just an arbitrary position vector, has Cartesian coordinates x, y, z. So if you were to expand out the dot product and square everything, you would end up with x squared, y squared, and z squared terms. So that's a quadratic term. Do we have any other quadratic terms in x, y, and z? Well, on the right-hand side, you've got modulus of r squared, which is just x squared plus y squared plus z squared, right? So you've got two quadratic terms, so it would make sense to me to move those next to each other. Let's keep the first one as it is. Just have r dot n squared. The other one's going to acquire a minus sign, so minus cos squared alpha modulus of r squared. So quadratic terms grouped together. Do we have any linear terms? Well, on the left-hand side, this big term here only has a single r in it. So if you were to expand all of that stuff out, it would be linear in x, y, and z because of this r here. Similarly, on the right-hand side, by the same logic, the final term is linear. If you were to expand out this dot product, you just get x's, y's, and z's. So we're going to move the linear terms next to each other. We can actually do some factorizing as well. I'm going to take out a factor of 2r because both terms have a 2 and an r in them. The term that was on the right-hand side is going to become positive, and you're going to get a cos squared r naught. We actually need a dot in front of our brackets here because we're dotting r into each term. So 2r dotted with, firstly, cos squared alpha times r naught. The second term is the one that was originally on the left-hand side, so it's still negative. Your scalar contribution, r naught dot n, just stays as it is. So we're going to take away r naught dotted with n. Then we need to put the vector n here so that this r gets dotted with this n and gives you r dot n as we originally had. So we factorized grouped those terms together. Finally, we've just got some constant terms left. We've got r naught dot n squared, and we've got cos squared alpha modulus of r naught squared. Those are constant because for a given problem, we consider r naught to be fixed, right? It's just the fixed coordinates of the vertex of the cone. It's x naught, y naught, z naught, which is different from x, y, z. So I'll put my constant terms at the end. Let's do it as just plus r naught dot n all squared, and then minus cos squared alpha modulus of r naught squared, and all of that stuff is now supposed to be equal to 0. Now, so far, what we're working with is still just the vector equation of a cone, right? We haven't said anything about conic sections. So now we can start thinking about how to actually take this equation, take a slice out of it, two-dimensional slice. And the simplest thing to do is find the intersection of the cone with the xy plane, right? It's perfectly possible to find the locus of points, which is the intersection of the cone with some arbitrary plane defined by some arbitrary normal. But to keep the algebra manageable, simplest thing to do is just choose the plane that you are intersecting the cone with to be the xy plane. We can do that without losing any generality, right? Because if we were to find the intersection of the cone with a different plane, we would be moving our plane around, but that's equivalent to moving the cone around, and we can move the cone around by changing r naught and n and alpha. So it's perfectly general to slice it in the xy plane. So all that means is that the z coordinate of our arbitrary position vector r is 0. So it implies that z is 0. That implies that the vector r only has x and y components, so it's just x, y, 0. Another useful fact is that the modulus squared of r, let's write this down, so modulus squared of r is just x squared plus y squared because it has no z component. That's useful because it appears in the equation on the line above. Another useful simplification we can make is to figure out what r dot n is, because that appears in our equation above. So r dot n, well, it's just a dot product. You multiply the x components of the vectors together and the y components and the z components, and you add those together, but there is no z component. So this is just equal to x times the x coordinate of n, which I'm going to write as nx, and then we just add on y times the y coordinate of n, and in the equation above it really appears in squared form, so we may as well square that now. So r dotted with n all squared is, well, you're going to get an x squared term, which has a coefficient of nx squared, so nx squared, x squared. Similarly for y, all right, so ny squared, y squared, and then you get your cross term, which is twice the product of this and this. So it's plus 2 nx ny xy. So we're now in a position where we can get a Cartesian equation for our conic section. It's not going to look that simple, but it's a start. So if I just call this equation star, think about what equation star implies, given that we're slicing it in the xy plane. So as we were saying earlier, general conic section is going to be quadratic. In other words, it's going to have terms up to and including x squared and y squared and xy. So let's think about all the different terms you're going to get. And let's deal with the x squared term first. So let's write down x squared and figure out the coefficient. Well, the first place you're going to get an x squared term from is the r dot n squared. We've just figured out that that has an nx squared x squared term. So your x squared coefficient will start with nx squared. You're also going to get an x squared term from the minus cos squared alpha modulus of r squared, because modulus of r squared is x squared plus y squared. So you're going to have to subtract cos squared alpha from your coefficient of x squared. Now, by exactly the same logic, you're going to have a y squared term. It's all symmetrical in x and y. And your coefficient is going to be ny squared, again, minus cos squared alpha. The other term, which is second order overall, is the cross term 2nx ny xy. That's second order because, well, x and y have a power of 1 each, and therefore the overall power is 2. So I'm just going to put that over here and give it a plus sign. Now the term which is linear in x and y is basically this big term that we factorized, and that's easy to expand out. All we have to do is replace each vector by its x component and then replace each vector by its y component and add those two things together, because that's how dot products work. So your first bit is going to be 2x. You're going to have cos squared alpha, let's say x naught for the x component of r naught. The scalar bit, again, just stays as it is. It's just r naught dotted with n. And then we take the x component of n instead of the vector n, like that. So that's our x bit. Then we just add on the equivalent bit for y, right? So plus 2y. You're going to have cos squared alpha times y naught, the y component of r naught. And then we're going to take away r naught dotted with n times the y component of n. That takes care of our linear terms. And there's nothing more we can really do with those constant terms at the end, so I'm just going to copy and paste them like that. So we've got this big 3-line Cartesian equation of our general conic section. So I've just kept the equation that we've got so far at the top of the screen, and what I want to do is rewrite this in a very simplified way, where we just give each coefficient of each x, y term just a letter. So what I mean by that is just going to write it as ax squared. Going to put the cross term next because that's the standard order to write the terms in. So plus bxy plus cy squared, right? Of course, there's a linear x term, so plus dx, a linear y term plus ey, and then our constant term, let's just call it f. So all of that is equal to 0. And I've just written below the parameters a to f in terms of the parameters of the cone. That follows very straightforwardly from the equation at the top. So I didn't want you to have to watch me take time to write all of that stuff out, but that should all be fairly self-explanatory. So one question which I think is interesting to pause and consider at this moment is whether the coefficients a to f can vary independently of each other. Now, the reason that I don't think it's super obvious the answer to that question is if you look at how a, b, c, d, e, and f are related to the parameters of the cone, you'll see that, for example, nx appears in several different places, so does ny, so does r naught, and so does alpha. And so could it be the case that there's some constraint that a, b, c, d, e, and f have to obey, or can they really vary completely independently of each other? I think the easiest way to answer that is think about the number of free parameters that we are free to vary with our cone. In other words, the number of degrees of freedom that we have. So what I mean by that is, well, r naught is completely arbitrary, right? Like you can put the vertex of the cone wherever you like. So I'm going to write down r naught, and r naught has 3 independent parameters. It's x, y, and z coordinates because we're in 3-dimensional space. So there are 3 parameters that you can vary independently by changing r naught. What about the vector n? Well, you might think that the direction vector of the cone also gives us 3 parameters because we're in 3 dimensions. Actually, it only gives us 2 because we have assumed from the very beginning that n is normalized, right? So an arbitrary vector in 3D has 3 degrees of freedom, but when you normalize it, you're removing 1 degree of freedom from the problem because it can't have whatever length you want. You can specify n completely by 2 angles. It's a direction vector. It only has 2 independent parameters that can vary. And then, of course, we've got alpha, the opening angle, the half opening angle of the cone. That's just a scalar. That's just one value. So in total, we have 6 parameters that can vary independently of each other. Now, a, b, c, d, e, f is, of course, 6 parameters as well. And so because you have 6 degrees of freedom, you can indeed choose any combination of A to F that you like, and that any given selection of A, B, C, D, E, and F must correspond uniquely to some particular choice of parameters of the cone, because we have 6 degrees of freedom. So I've kept our simplified conic section equation at the top there, and I've just kept the definitions of A, B, and C, because for the rest of the video, we're not actually going to care about D, E, and F, but A, B, and C are going to be turn out to be the most important coefficients for our purposes. And what I want to do is just introduce a certain quantity. I'm going to say, let's consider something which I'm going to define as delta. This is the discriminant, and it's going to be defined to be b squared minus 4ac. This should look familiar from what you probably already know about quadratic equations. Right? This is for a quadratic equation, the quantity b squared minus 4ac tells you about whether you have 0, 1, or 2 real distinct roots of your equation. It turns out that this analogous quantity b squared minus 4ac for our conic section equation actually has a very interesting geometrical interpretation. So let's figure out what delta, the discriminant, is equal to in terms of the parameters of the cone. So b squared is just going to be 4nx squared and y squared. We're then taking away 4 times, well, a, which is nx squared minus cos squared alpha, multiplied by c, which is ny squared minus cos squared alpha. So we can expand the brackets and see what happens. Well, firstly, notice that one of the terms you get when you expand the brackets, the first term you get is going to be nx squared ny squared. That's going to have a minus 4 put in front of it by that prefactor. And so that is going to make the 4nx squared ny squared at the beginning of the right-hand side disappear. Right, so that's nice. 2 terms cancel. What terms are we going to be left with? Well, you're going to have nx squared times minus cos squared alpha, then times minus 4. That's going to be positive overall. So 4 nx squared cos squared alpha. You're going to get a similar term, but with ny squared instead of nx squared. So plus 4 ny squared cos squared alpha. And then your final term, the only one we haven't accounted for yet, is the one where you times the 2 cos squared alphas by each other. So these minuses will become positive, but then you've got a minus 4 at the front. So overall, we've got minus 4 times cos to the 4 of alpha. Now, there is a common factor in all of these terms of 4 cos squared alpha. So I'm going to factorize that out. So 4 cos squared alpha, you're going to get nx squared from the first term. You're going to get ny squared from the second term, and you're just going to get minus cos squared alpha from the third term. So what are we going to do about this nx squared plus ny squared bit? Well, I've just sketched out this little diagram where I've represented the direction vector n as a point in some Cartesian coordinate system, and this looks very much like the standard diagram that you may have seen when you're converting between Cartesian coordinates and spherical polar coordinates. So what I'm going to do is define the usual angle phi, as we do in spherical polar coordinates. The usual theta in spherical polars would be defined relative to the z-axis. I'm going to define a different but related angle here. Instead of measuring n relative to the z-axis, I'm going to measure its angle relative to the xy plane. So I'm going to draw an angle like this, and let's call that gamma. Of course, you can give that angle whatever symbol you like, but whatever you decide to call it, defining the angle relative to the xy plane rather than relative to the z-axis makes the discriminant a little bit easier to interpret. And the reason is basically that, remember, we're slicing our cone in the xy plane. So the angle that n makes relative to that plane is of great geometrical significance for what we're doing here. You can then just do some trigonometry to work out how to express n in terms of those angles. The modulus of n, remember, is 1. It's normalized, so we don't have any prefactor. Firstly, you want to project n into the xy plane to give this length here. That is just going to be cos of gamma in this, well, using those angles that I've defined there. So you've got cos of gamma, projecting it into the xy plane. Then to project it onto the x-axis, you're going to have to multiply it by cos phi. Similarly, to project it onto the y-axis, you have to times by sine phi, so cos gamma sine phi. And the projection onto the z-axis is simply just going to be sine of gamma. So there is our direction vector expressed in terms of those angles. And the combination that we ultimately care about is nx squared plus ny squared, because that appeared in our discriminant. Both nx and ny, the x and y components, have a cos gamma. So when we do this, we're going to get a common factor of cos squared gamma. then we're going to factor out cos squared phi plus sine squared phi. But then, of course, we have an identity that tells us that the bracketed bit is just 1. So nx squared plus ny squared is the squared cosine of the angle that the vector n makes with the xy plane. So that allows us to rewrite the discriminant delta in terms of gamma rather than in terms of the individual components of n. So you've still got your prefactor of 4 cos squared alpha, but the nx squared plus ny squared bit is now, well, cos squared gamma, and then we take away cos squared alpha from that. So this is certainly a nice looking expression that our quantity b squared minus 4ac simplifies to. But what can we actually learn about our conic section by considering this quantity? So we're going to consider 3 different cases, as we do with quadratic equations, where the discriminant is 0 or positive or negative. And I want to start by considering the case where your discriminant is 0. So if delta is 0, that implies that cos squared gamma minus cos squared alpha is 0. Now, of course, that equation has infinitely many solutions for alpha and gamma, but we're only going to consider angles between 0 and pi over 2. And so we're sticking to the first quadrant, and that means that alpha and gamma have to be the same. Right? If their squared cosines are equal, then alpha and gamma have to be the same. So I'm going to write that down. If the discriminant is 0, that tells you that alpha is equal to gamma. So geometrically, what does that really mean? Well, I've just drawn a little 2-dimensional cross-section of our cone there. I've drawn on the half opening angle alpha. This dashed line represents the axis of symmetry. So the dashed line is basically the vector n. Now, remember that gamma is the angle that the vector n makes with the xy plane. So what we can do is draw our xy plane onto this diagram. That could look something like this. And the angle gamma there is, of course, is the angle between that plane and the axis of symmetry n. And so it's that angle there. Now, it's no coincidence that I've drawn the red line there parallel to this line which defines one of the surfaces of the cone. They have to be parallel to each other in this case because alpha and gamma are the same. Now, by definition, if you choose to slice your cone parallel to one of the lines that defines one of its surfaces, what you have is a parabola. And so to summarize all of this so far, we've said that if you just take some arbitrary equation, ax squared plus bxy plus all of that stuff, you calculate the quantity b squared minus 4ac. If you get 0, that means geometrically that you've sliced your cone parallel to one of the lines that defines the surface, and therefore you have a parabola by definition. So what about the other cases? Let's say case 2 is going to be the case where the discriminant is negative. So delta is less than 0. So if delta is less than 0, that implies that cos squared alpha is bigger than cos squared gamma. Equivalently, cos alpha is bigger than cos gamma. But because cos is a decreasing function in the first quadrant, that implies that gamma should be bigger than alpha in order for cos gamma to be less than cos alpha, right? This is implying that gamma is bigger than alpha. Let's try to do a sketch and visualize what that actually means. So if you imagine taking that diagram that we had for our parabola and rotating the xy plane, which is the red line, rotating that around anti-clockwise, I guess, so that gamma becomes bigger, you'll end up with something that looks a little bit like this. I'll try to make it very clear that gamma is bigger than alpha. The angle gamma here is this one here, right? So you can clearly see in that diagram, gamma is bigger than alpha. And you can see that our xy plane cuts through both sides of a little cross-section of our cone. What that means, if you can picture this in 3 dimensions, is that the conic section that we get, the locus of points, which is the intersection between the plane and the cone, is going to be a closed loop. And when it's a closed loop, we say that is it's an ellipse. Now you can probably see where this is going. So I've already written out case 3 for you. We've got a diagram here. This time, if the discriminant is bigger than 0, cos gamma has to be bigger than cos alpha, which means gamma is less than alpha. So angle gamma is smaller than angle alpha. That implies that your xy plane, the red line on this diagram, now intersects the cone on both the upper and lower branches, right? That kind of curve is called a hyperbola. It's the only type of conic section that has 2 separate branches, because that's the only case in which your xy plane intersects both the top and bottom branches of the cone. So those are the 3 cases that you can distinguish between just by considering the sign of the discriminant. There is an interesting 4th case, which I think is worth considering, which is basically a special case. And this is what happens when the x and y components of the normal, the direction vector, the axis of symmetry of the cone, when those components are both 0. So nx equals ny is 0. If we look back at our definitions of a, b, and c up there, if the nx and ny are both 0, that implies firstly that a is equal to c because they're both minus cos squared of alpha. It also implies that b has to be equal to 0, right? So if both of those components are 0, then that implies that a equals c and b equals 0. Geometrically, what's the significance of that? Well, nx and ny are both 0. That means nz has to be 1, or I guess minus 1, because it has to be normalized, doesn't have any components in the x and y direction, so it's purely in the z direction. So your axis of symmetry is parallel to the z-axis. I'll say it's parallel to the z-hat vector. Now, because the z-hat vector is perpendicular to the xy plane in which we're doing the slicing, that means you're taking a slice out of your cone in a plane which is perpendicular to its axis of symmetry, and if you can visualize that in 3D, that corresponds to a circle. Now, we don't always sort of give this its own special status like parabolas, ellipses, and hyperbole, because a circle can be thought of as a special case of an ellipse, but we can take it a little bit further. If a is c and b is 0, then we must have a circle. Okay, I think that's enough on conic sections for this time. Thanks for watching. Hope it's been interesting, and see you again soon.